Nashville's first webinar 2022. My name is Katie Poss, and I am the co-chair of the CLF Nashville Hub alongside Nicole Ritter with Gresham Smith Architects. The Carbon Leadership Forum at the University of Washington is accelerating the transformation of the building sector to radically reduce the embodied carbon in building materials and construction through collective action. They pioneer research, create resources, foster cross-collaboration, and incubate member-led initiatives to bring embodied carbon emissions of buildings down to zero. I encourage you to visit carbonleadershipforum.org to learn more, and also encourage you to join our Nashville Hub community on LinkedIn. If you're interested in helping to develop case studies or have a proposed topic for a future session, please reach out to me or Nicole. We'll drop our email addresses in the chat. Just so everyone is aware, today's session will be recorded and it will be later posted to our YouTube channel. If you have questions, please drop those in the chat as we go through the presentation. And without further ado, I'll hand it over to today's all-star lineup. We have Kim Shinn, Principal and Sustainability Wizard, and Cory Duggin, Principal with TLC Engineering Solutions, and William Paddock, Co-founder and Managing Director at WAP Sustainability.
Thank you very much, Katie. I'm going to take off and start the presentation. This is really an introduction into one of the new initiatives of the Carbon Leadership Forum, the MEP 2040 Challenge. So the agenda today is like I said, kind of a 30,000-foot overview of what's going on with the MEP 2040 Challenge. We're going to talk about what are the main pillars of the challenge, and then get a little bit into the nuts and bolts of what's going on with the challenge, and then hopefully leave some time for some questions and answers. The issue that a lot of the material is around is the MEP system. So we're going to try to avoid going in too far down into the nerdy weeds of what MEP systems are, and really try to keep this mostly at the level of the carbon impact. So the MEP 2040 Challenge is really kind of a companion to the AIA 2030 Challenge and Commitment. And this started more than 10 years ago with Ed Mazria coming out and saying, you know, as the built environment industry, we need to figure out a way to get our operational carbon down to net zero by 2030. So when he came up with the challenge, he gave us kind of a stair-step 5-year by 5-year goal of decreasing operational carbon. And now in the period between 2020 and 2025, now we're at 2022, we're trying to get down to almost zero carbon at that point. So you can see that the sort of dark orange bars are the amount of operational carbon that's left in the building, so that by 2030 we've hit zero on the operational carbon, and the lighter orange bars are actually renewable energy offsets that bring us down to that net zero, understanding that there's probably some operational carbon that's left in buildings, and you're using either on-site or in a combination of off-site renewables to get that down to a net zero. And then our friends, the structural engineers, had been kind of feeling left out of the green building game for some time, and they said, oh, embodied carbon, this is a place where we can start making a difference with our big structure, all that mass that's in a building. And being the conservative type guys that they are, they said, we're going to try to get to net zero embodied carbon by 2050. Therefore, structural engineers 2050 challenge and / commitment. So you could see that they've also got a stair-step goal for getting the dark blue part of their embodied carbon part of the building down to 0 by 2050, with the renewables in the lighter blue boxes being the offset to get what's left of the embodied carbon of the structural systems out of the building. The part that I left out here is the open white bars are actually more efficiency. So in looking at the white bars in the structural engineers part of the game, this is actually them figuring out ways to put less carbon into their buildings in the first place. So more efficient structural systems, working with the other members of the building team to decrease the need for so much mass in the structural systems. This is their way of getting more efficient in that world of decreasing their embodied carbon, while most of the dark blue is associated with better material choices. So the MEP 2040 challenge is essentially the companion to that. On the operational side, we're already kind of wanting to be on the same track with the architects. So the architects established this net zero goal by 2030. That's where we're going to play along and be in the same trajectory with the architects, and then embodied carbon getting down to 0 by 2040. And then once again, seeing those open white bars as less material to begin with in terms of embodied carbon, and then the lighter green bars being the renewables that offset the remaining embodied carbon that's left in the buildings. So we want to be integrated and hand in hand with the rest of the building team in getting down to those net zero targets. And hopefully our structural engineering pals will be emboldened and see a great deal of progress, and they'll join us in getting there to 2040 net zero. So far, and in our first less than 6 months actually in existence is the MEP 2040 challenge. The folks in the top here, these are the logos of the roughly 30 signatory firms. These are signatories are MEP design firms, either MEP consultants or A&E firms with a substantial MEP practice, who have signed on to the challenge, while the supporters are associated partners in the industry: architects, contractors, manufacturers, professional associations. So you can see that the AIA in the 2030 or the Architecture 2030 Challenge, Ed Mazaria's group, have already jumped in there. Will's firm, WAP Sustainability Consultants, is one of our supporters. And then here on TLC, we're signatories as well. The big statement is that the challenge compels us to advocate for and achieve net zero carbon operationally by 2030, and then embodied or whole life carbon by 2040. There are essentially 4 different major activities that form the challenge, and in a lot of ways we're taking our script from what AIA 2030 commitment and the SE 2050 commitment are doing, and tailoring our program to look pretty much like that. So the first pillar is basically having a plan to get there. The second and third are really specific to the MEP world in terms of refrigerants, and then getting more data on the embodied carbon in our materials and equipment. And then the fourth pillar is essentially a commitment to participate and to share knowledge with other members of the 2040 challenge, both of the signatories and the supporters. So there's a real sense of collaboration that I find really exciting. Our industry, the MEP consulting industry, has traditionally been very, very competitive. We didn't want to give away any of our, secret sauce recipes to our competitors, because we didn't want them to get clients that we already had, or to win jobs that we compete on. We've come to realize that in this world of trying to do something about the building industry's impact on climate change, is we can't afford not to get into this game together and to make sure that all of us win this race to keep climate change from getting out of control. Interestingly enough, if you look at the color scheme of the MEP 2040, it brings to mind maybe some current events that are going on. Certainly a valiant struggle that takes a lot of courage and a lot of commitment to get to where we want to go. And I urge you to visit our webpage on the Carbon Leadership Forum website to look at the resources that we're going to be putting up there, to get more information on what's going on with the 2040 challenge. So the first thing is to create this company plan, and that's basically a roadmap for you to get to this goal of operational net zero by 2030, whole life embodied carbon by 2040. It compels you to advocate for, once again, your projects to achieve these goals. Now, the thing about decarbonization is it's not just the end goal, it's also the journey. So we're not telling people that you've got to get there the moment you sign onto the commitment. You're given the opportunity to establish a company plan that puts you on the path to getting to those goals. So however you as a company want to structure those, it's really up to you. What we ask as a part of the commitment is that you keep score, that you gather information on how your projects are designed to perform, and optimally how they actually do perform, that you reach out to buildings and projects after they get into operation to see how they're doing. That's really the essence of what this company plan piece is set up some goals and get your plan together for how you're going to do that. And then, as I said before, start keeping score. How do your projects go in terms of reducing their operational carbon and their embodied carbon versus the goals that you've set for those projects? One of the things that I think is pretty interesting, once again, it's this idea of getting everybody on the building team to work together, is our friends at the AIA have for some time had a operational carbon reporting platform as a part of the AIA 2030 commitment. It's called the DDX, the Direct Digital Exchange. Basically it was a place to enter information on a project by project basis for operational energy and then translating that into carbon. Just recently, in the last couple of years, the DDX has started to add embodied carbon reporting. And one of the interesting things is that a lot of MEP firms, in helping their architectural partners and clients do the reporting associated with the AIA 2030 commitment, we were already putting a lot of information about those projects into the DDX. And the AIA has been really generous about talking with the MEP 2040 Challenge about using that same reporting structure rather than us come up with a unique reporting tool. We might be able to use the DDX to do our reporting. Another big difference between the MEP 2040 Challenge and what's going on with SE 2050 and the Architecture 2030 Challenge is the reporting format for the structural engineers is actually being hosted by the American Society of Civil Engineers Structural Engineering Institute. That's the professional organization is actually hosting the reporting for people who have signed on to the SE 2050. The AIA maintains this reporting platform for its member organizations in the AIA 2030 commitment. Here in North America, we don't have a single professional body that is the host of building systems engineers. In the UK, for instance, there's something called CIBSE, the Chartered Institute for Building Systems Engineers, CIBSE. CIBSE is their professional organization. Here in North America, we're kind of fragmented. We've got the plumbers over here and the fire protection guys over there and the electrical guys back here and the mechanical folks have got ASHRAE. Right now, we don't have a single professional host for this. So we're kind of piggybacking. The idea would be to piggyback the reporting piece through the AIA. There's nothing that says that a company that signs on to the MEP 2040 Challenge can't come up with their own reporting gizmo. So I'm going to hand it over to Cory to talk about the refrigerant pillar, and he will instruct me to advance his slides.
Thanks, Kim. And I think it's design data exchange.
Okay.
Close enough. So, well, thanks, Kim. And so we're going to start to jump into, what are some of those pieces that are going into, the embodied carbon of MEP equipment. The first one of those we're going to look at is the refrigerant, the sort of the magic sauce that makes the cooling happen. And you can see here the life cycle of a refrigerant, right? So we're starting out from production to supply, to transportation, to going into equipment, and then there being basically a cycle that while the equipment is in use, there's some of it that's constantly, being leaked and has to be refilled. There's inherently, leak risks. Every time that you're charging or discharging, gas from a piece of equipment, you have that, little bit that gets blown off, from the pressure release there, as well as, there's always the potential risk when it's being transported. And at some point, there's going to be some sort of end of life destruction, but hopefully a lot of it, when equipment gets taken out of the field, can be reclaimed, put back into that supply line so that we're not having to produce as much refrigerant, and we can kind of, create this cycle without having to add a whole lot to it. Next, please. So where does the refrigerant piece of the embodied carbon show up here in this overall embodied carbon operational impact? And so it shows up in the B1 use stage here, which I think a lot of folks think that, well, because it's part of the MEP equipment and the MEP equipment is so associated with the operational energy and the energy that equipment uses, that's where it would be. But because that we're really talking about the refrigerant from manufacturing to being charged at the factory to being recharged in the field, that's really part of the B1 use stage of equipment, while the building is being used through there. Next, please. So where we're looking at is that, like we talked about, that we have refrigerant that's installed in equipment in the field. As that equipment is used over its lifetime, some amount of that refrigerant, slowly leaks, whether that's, through pipe fittings or what have you. That, that's why that periodically your air conditioner at your house may stop working as well, and you have to have someone come out and put a little bit more refrigerant in. That's because of, maybe some slow leak there. There's another piece of the, embodied carbon or carbon for the MEP equipment is that's the operational carbon. So like we talked about, that's the energy that the equipment is using to produce that cooling effect, to, turn the fans, to run the pumps, to move the compressors, to create that cooling effect that we use to air condition our buildings. And, that comes down to, mostly, scope 2 or scope 1, depending on how it's being done, emissions. That, we're looking at what's going into it at the power plant to create the electricity to turn those compressors. Next. So here you can see, where the different pieces of that come together from scope 1 to scope 2 to scope 3. So that operational piece, what is happening, at your house, at the physical office building, whatever the company owns, that is your scope 1 emissions there. And, the fugitive refrigerant is what we call the leaked refrigerant, whether that's, during operation, or whether that's whenever the system is being recharged, or whatever's maybe, lost whenever a piece of equipment is replaced and that we try to recover, that there's some percentage loss there. There's also potentially some, in scope 1 or in scope 2, depending on, if you were to have district chilled water, then that may push some of those refrigerants out to a plant or a utility that someone else owns. Then those wouldn't necessarily be under your scope 1 emissions. Those would be pushed out to scope 2. And you can see here how the EPA defines scope 1 and scope 2 inventory. And really it comes down to that scope 1 is emissions from sources controlled or owned by the organization, right? So it's what that organization owns and operates, for their facility. Next. So how big a piece is this, and how does it really play in with the operational carbon? So you can see, starting on the left here, we've got our operational carbon coming in with power input from the grid, with the orange being that refrigeration leak piece that we've been talking about, whether it's at beginning, operation or end of life, and then the gray being the manufacturing and end of life piece for the physical equipment itself. So as the grid becomes cleaner and carbon free, we're going to pull that power input carbon impact out of the grid and be really minimized there to where we're essentially at 100% renewable power. You can see at that point now, the refrigeration leak piece has become the largest piece. So as we push to decarbonize, we're going to be left with, a piece of the pie that we really need to be working on minimizing if we're going to get to truly, decarbonizing our buildings. Then as we move further, we move to low GWP refrigerants. You can see that we minimize that. And then hopefully eventually we can move to no GWP or refrigerants to where we're left with essentially just, the little bit of power input from the grid that should be 100% renewable at that point, less some sort of losses in transmission, and the manufacturing and end of life pieces, just really to produce the physical pieces of equipment and transport it to the site. So what refrigerants are good, what refrigerants are not so good? This chart, I think, does a really good job of illustrating the relative impact of different refrigerants. So probably the ones that you see the most often, and these are ones that are commonly used in large refrigeration equipment like centrifugal chillers. So R134A is a very common refrigerant. It was, I believe, a replacement for R22 back in the day. And so it has a global warming potential of 1430, as you can see here, to just kind of give a scale to these bubbles. Now, R123 was one that was phased in for a little while, but it doesn't have a ODP or ozone depletion potential of 0 like some of these others do. So we've actually moved away from it. But the ones that you see that are the really small bubbles here, the 1, 2, 3, 4 ZE and 1, 2, 3, 3 ZDE and the 514A, those are some of our new low global warming potential refrigerants. So in a lot of chillers today, we're seeing them moving from this 1430 orange R134 bubble down to a 1233 ZD or R514A. And you can see how significant the difference is in global warming potential here. I mean, we're talking about, 1430 versus I believe that R514 has a global warming potential of 2, right? So significant impacts in how just in the selection and advocating for these lower global warming potential refrigerants, the impact that we can make on the embodied carbon going into our buildings and, what goes through the life cycle of this equipment. Next, please. This graph has shown us that, we were talking about recovery and that over the past, 3 or 4 years, well, I guess it's longer than that now, it's 2022, right? So it's like over the last 5 years that there's been, a 20% or even more now potentially, since this is only through 2019, increase in collecting reclaimed refrigerants at end of life. So you can see that, we're not doing so good previously, and now there's really been a tick up of us starting to reclaim that. And so if it wasn't being reclaimed, then where was it going? It was probably being off gas straight into the atmosphere. So, this is another way that increasing what gets done from a reclaim standpoint helps to keep those refrigerants in the life cycle being reused and not going into the atmosphere and, creating global warming. Next. So of the total global emissions that we're talking about, whether it be, direct CO2, either from industrial and fossil fuel or methane or nitrous oxide, F gases, or what we typically refer to as refrigerants, are about 2% of those global emissions. So in terms of that, maybe not huge, but in terms of the impact we can have in buildings, maybe larger. And of that 2% of those F gases, the largest portion of those is the HFCs, so the hydrofluorocarbons. You can see that the other types here, very small in consideration. So that's really the piece that we want to focus on, because obviously it's going to have the largest impact in our ability to reduce those emissions. Next. So there's a few refrigerant data sets out there for both life expectancy, refrigerant leakage, because all leakage is not the same. Different groups have different estimates and opinions as to how much leakage you should assume throughout the life and operation of a piece of equipment, as well as the environmental metrics for the refrigerant itself, whether that's coming from LEED or ASHRAE or the EPA. Thanks. So let's go into an example here and just see what kind of impact we're talking about. So we're looking at an air-cooled chiller using R410A. The life expectancy of the building is 60 years. The life expectancy of the chiller is only 20 years, right? So over the lifetime of the building, we're going to have 3 of these chillers to keep it running. So each chiller arrives with 48 kilograms of this R410A refrigerant. So that's what we're starting with. And then over the lifespan, at installation, we're assuming there's a 1% leakage. Annually, about 15% gets leaked. And then at the end of life, we're able to recover 95% of that refrigerant. So that's, 5% not getting recovered of the total charge in the machine. And we're assuming that at end of life, it's at full charge, right? So the global warming potential of this refrigerant is 2,088 equivalent kilograms of CO2 per kilogram of charge. So that gives us, what the impact is going to be for this piece of equipment. The ODP for 410A is 0. So if we take that, do a little math here, and take our initial leakage at installation, annual leakage over 20 years, because that's the life of one machine, add that to the end of life recovery, emissions, we've got about 147 kilograms of lifetime refrigerant that is being leaked to the atmosphere. That comes to 306,000 equivalent kilograms of CO2, which is the same as about 34,500 gallons of gasoline being consumed by a car, or 56 homes worth of electricity per year. So pretty significant just for, a little bit of gas being leaked. But now if we take that a little further and we look at the lifetime refrigerant leakage for the life of the building, so now we're looking at 60 years in 3 of these machines, that brings us up to 920,000 equivalent kilograms of CO2, which is 103,000 gallons of gas, 167 homes, or 2,100 barrels of oil. Pretty staggering. So now let's take this a step further and see how we compare. So we've been talking a lot about the refrigerants. There's another piece that we talked about, and that's, the materials, the embodied carbon to both, produce and transport this chiller to the site. So that from A1 to A3, so manufacturing transportation is about 43 kilograms. So with the total GWP emissions for A1 through 3, assuming 3 chillers, right? That's giving us 14,190 equivalent kilograms compared to our 920,000. So pretty small. I mean, it's really about 1.5% of the total refrigerant GWP emissions is the embodied carbon from materials. So the reason we point this out is that where the embodied carbon of the equipment is important, it's not nearly as important as choosing a good low GWP refrigerant and making sure that there's insulation to minimize leakage, right? Because the impact there is so much larger. Taking that and comparing it to the building embodied carbon and see, okay, now we've looked at this chiller from the refrigerant to the materials, and now if we compare that to its piece of the total building's embodied carbon. So the average GWP, according to ILFI, for the typical building stock is about 600 kilograms of CO2 per square meter. So that gives about 1.8 million kilograms of CO2 for the total building stock in embodied carbon. The operational carbon, if you're taking an office building in Seattle, assume it has an EUI of 42. Make some assumptions about the emission rates. In this case, we're using the Northwest for Seattle, using ILFI numbers. The lifetime carbon is about 8.1 million kilograms of CO2. So if we compare that to the refrigerant embodied carbon is 920,000. So these embodied carbon numbers from the ILFI don't include the refrigerant, because previously we've never been including, embodied carbon for this, because there really wasn't data for MEP equipment, and even on living building projects, you didn't have to account the embodied carbon associated with the refrigerant. So this 1.8 million kilograms that we're talking about over here, that's not including the refrigerants that are in any of this. So if we start to do that, 50% of the total embodied carbon is from the refrigerant alone. That's including the steel, the concrete, all of that really heavy material that we think about as being, big pieces of the embodied carbon. The refrigerant alone is 50%, bringing up to 11% of the operational total. So it's pretty staggering when you see and start to compare how big a piece the refrigerant has of the total and the impact that can make.
Sort of a thing to think about is that refrigerant piece is, as Cory said, is something that we've just kind of been neglecting in our previous embodied carbon stuff. And we're now just beginning to think about the embodied carbon associated with actually putting the the pieces of equipment and the materials, the pipe, the ductwork, those sorts of things into the building that are part of the MEP systems. And in order to start putting numbers on what those embodied carbon numbers are, is we need to get information from the industry about what the embodied carbon of those materials and equipment are. So that's where Will's going to be talking to us about getting that information out of the industry. Will?
Yep, great. Yeah, I mean, you hit it on the head. I mean, whether you're a project team, a designer, a structural engineer, MEP engineer, a manufacturer, all the numbers that Cory just described all had to come from somewhere. And all of this sort of analysis on embodied carbon and operational carbon and total carbon, it's all influenced by data somewhere. Kim, you had a slide early on about the different the relationships between like AIA SE 2050 and then MEP 2040 and the amount of carbon. And I think that really, those sort of linear, the percentage of the pie charts sort of change depending on building type. And so sometimes the mechanical and electrical, especially in like a data center or something like that, are actually very significant. Healthcare, very significant. Anything heated and cooled compared to, I think the embodied carbon conversations that we tend to key up on a lot of buildings, especially from a core and shell and a structural engineer standpoint on concrete, steel, glass, things like that. So in my experience and looking at embodied carbon in buildings and different building types, and then also understanding the carbon footprint of different building products, we're seeing that sort of insight can really change. And so depending on building type, the most material embodied carbon topic may change, category may change. So as Kim mentioned, I'm William Paddock. I run a company called WAP Sustainability, and in the building sector, we're known a lot for our work in creating and conducting life cycle assessment. So we fit the moniker of a life cycle assessment practitioner. And then most of our work then falls into working with program operators to create environmental product declarations. So we'll talk primarily around EPDs today because those are the physical, tangible PDF thing that lives in the world. To draw a parallel, life cycle assessment is the accounting exercise. So it's the conducting the numbers. The EPD is the reporting vehicle. So LCA data flows into EPDs. And so I sort of see my logo on top of the UL, SCS, ASTM, and NSF because we're upstream of that. And we work with manufacturers directly to create the LCA data that then gets verified by one of these recognizable logos. So that's we'll talk in this little segment on what are EPDs, why EPDs are important, a little bit on the types of EPDs that are available, how you kind of start the process, and then how that's going to kind of look and feel for equipment manufacturers in MEP space as a result of MEP 2040. So as I mentioned, EPDs are transparent, objective reports that communicate what a product is made of and then how it impacts the environment across the entire life cycle. So when we talk about embodied carbon, we're typically talking about the product as delivered to the job. So just this A1 through A3 definition. So use phase and some of the other end of life scenarios aren't really factored into the definition. They can be. But the document is intended to provide verified information. It's recognized by LEED. It's a component of IGCC. It's recognized by the federal government and a lot of different certifications. Cradle to Cradle, others recognize LCAs and EPDs. And again, it's that accounting exercise. So it's the work of a manufacturer to account for the carbon impact of its products. There's other life cycle impact categories like eutrophication and contribution to smog and other things like that are buried within the document. The primary utility, the bright, shiny object is the carbon value. And so that's the important. And the utility is pretty cool. So this example here of the ceiling panels from Armstrong, This is what a UL EPD looks like. They tend to have similar looks and feels depending on the program operator and who you're working with. They have a lot of standardized information that draws on some ISO standards like ISO 1425, 1440, 1444, ISO 21930. So they're grounded in internationally accepted protocols and methodology. They communicate and define things like the system boundary for a life cycle assessment. Again, where I was saying the A1 through A3 stages, or the product as delivered to the customer, and then things like use and leakage and end of life and materials sent to landfill. All that can be factored in as well. And then there's a table which provides, I think that's your next click, the values. So here, that second row is providing the carbon value of the product at production, at use, at end of life, and then in total. So you can see here the majority of the impact for this ceiling tile is in the production phase. So almost 90-something%. Use phase is pretty obvious. You just stick it in the ceiling and it doesn't do much. As compared to something that's mechanical or electrified, that number would be different. And then I think they're modeling some end of life recycling, why it's got a negative value. But this is the value, is you get context of carbon footprint and where it is. You could compare those Armstrong values to another product. If you wanted to buy lower carbon, ceiling tiles, maybe you're looking for somebody that has 20 kilograms or 10 kilograms or something of that nature. So that's kind of how these are being used. There's different types of EPDs. I don't want to get into the product specific declaration because there's probably 10 of those in the world. So just know that doesn't matter. Industry-wide EPDs do exist. This is where an industry association will work with its members. They'll conduct a kind of a weighted average value to determine like what's a normal carbon footprint for that industry, and publish that. And so manufacturers who participate in that get a lot of insight that can be really useful for industry associations and setting baselines and other things like that. And then the highest quality, the most specific, or what we call type 3 product specific EPDs. So as you saw in that Armstrong example, it's down to like Prelude, like the specific product family. It may contain some information on different thicknesses or different sizes, depending on what the functional unit is. But the idea is it's reporting the product as the product is sold. So if you call it something, then you should probably name the EPD after that product. Again, all of these with industry-wide or product specific, just to make this a little bigger, it's all built on a life cycle assessment that references a product category rule. Product category rules are something that get a little more complicated than need to be. There's pretty much product category rules for every product. And if there's not one on a specific product, then ISO 21930 functions as a product category rule for anything in a building. We do also want to make sure that as part of like lead requirements and other things, that these EPDs require to the ISO standards, which I rattled off. And then the beauty is it's a verified document. So the program operators of UL, ASTM, NSF, they go through a process of verifying the LCA data to making sure that it was conducted properly, and then making sure that the information contained in the PDF is factual. So they can be highly trusted in terms of their relevance as a source document. And I think if you click again, there's a product specific. Yeah. Okay. Well, so the first steps in getting an EPD is, you could say, look at the product category rule, but really the first step is to conduct a life cycle assessment. You have to do the accounting work in order to even move toward the stage of getting an EPD. This screen will pop up a product category rule. As I mentioned, there's and it's highlighting some of the MEP specific product category rules that exist in the world. There's PCRs in the US and North America and Europe. And so a talented LCA practitioner will help navigate and figure out what the appropriate PCR is for product. And so for MEP, there are some nuances that have to kind of be sorted. But just know it's not a massive barrier. There's ways to work through that. And then, so based on the product and product performance, conducting the life cycle assessment, and then moving toward the EPD. This slide I think is important. If I'm a MEP manufacturer, or I make something in that category, this is the chart of when you're probably going to be asked the most for these documents. So currently my world sort of looks like I live downstream of the ask. So when a project team or any of the people that are signatories to the MEP 2040 go to manufacturers and say, hey, I need EPDs on your products or else we're not going to purchase them. That's usually where we get keyed up, as somebody calls and says, hey, I got asked for EPDs from these 3 customers. And so I need to do it for my condensing units and my VRF product line. And so this will give you a sense of how this preliminary timeline for MEP 2040 is going to roll out between now and 2026. So if you want to be studious and get ahead of it, I'd be thinking pumps, fans, batteries, switch gears, and transformers and stuff like that early on. But this gives you a sense of kind of when products are probably going to be prioritized and asked the most. And then again, just when asked, follow the process of finding an LCA practitioner and working through getting EPDs. I would target product specific for just about anything, because that's going to have the longest shelf life for you.
A couple of interesting things about MEP equipment.
Sure.
So when we look at the life cycle of a piece of MEP equipment, most of the carbon associated with that piece of MEP equipment is actually in the operational phase. So one of the big challenges that we have in coming up with EPDs for building system equipment is defining how to calculate that operational phase in a sort of industry standard way, the product category rules, the PCRs. And one of the things that we want to make sure that people can really appreciate is, and it goes back to one of the pieces of data that Cory showed in his example, the embodied carbon, the A1 through A3, the actual, extracting, manufacturing, and getting it to and into the building, that's like 50 kilograms of CO2 equivalent. Whereas the operational carbon of that piece of equipment may be several thousand kilograms of CO2 equivalents over the life of that piece of equipment, over the 20-year life of that piece of equipment. So making a decision about selecting a piece of mechanical equipment based on that A1 through A3 carbon number is possibly, getting your blinders on a little bit too small. And when we bring in the refrigerant piece of that discussion, then it gets even more complicated. So I know a lot of us are really anxious to start getting a lot of this data in so that we can begin to do our life cycle assessments. The practical reality is that at least for the first few years of the 2040 challenge, we're going to be really challenged in coming up with good data for our life cycle assessments. And it's just a feature of the beast. Another thing to sort of be aware of is that in energy using equipment like chillers and pumps and transformers, the operational carbon tends to be sort of a function of how much heat transfer there is built into the piece of equipment. And heat transfer is actually material mass. So we could very well see a chiller have a much higher A1 through A3 embodied carbon, but a much lower B6 operational carbon piece. So like I said, don't get your blinders too small on that A1 through A3 piece. It's a big chunk of a piece of ceiling tile, but it's not such a big chunk of a chiller. So
Yeah, let me speak to that just a little bit, because a couple of things your point is so spot on, and I think there's definitely some evolution about like how are we thinking about embodied carbon? Is it just the A1 through A3 stage, where I talk a lot about like the EC3 ecosystem, which is really fostering a lot of like embodied carbon procurement decisions. The buy cleans of California's and Colorado's and others are purchasing based programs that say, here's a threshold and buy below the threshold. And so that A1 through A3 is being used for that. But once you step out of procurement and you say embodied carbon purchasing is not my primary focus, my primary focus is design or, whole building, then what we're really talking about is total carbon, which is embodied carbon plus operational carbon. And if we're too myopic on the embodied carbon procurement, we're going to make all sorts of stupid decisions, and we're going to have all these unintended consequences that come with low carbon procurement. Which, my example is, a car that has a very, very, very low embodied carbon footprint, but only gets 1 mile per gallon, is a pretty crummy vehicle. Insulation products are another kind of fun one. A product with the lowest embodied carbon footprint as an insulation product is probably a terrible insulator. And so you have these very obvious trade-offs that aren't fully unpacked yet, but this total carbon perspective is one that's really rattling and I think catching steam, because we're seeing these trade-offs as we start to use and think about embodied carbon information differently. The other one, Ken, you made a comment about like the PCR and LCA conversation, and we've been doing LCAs well before PCRs were done. And so what a PCR does is tends to bridle, what the LCA results are. And so some PCRs, state that the use phase or end of life doesn't have to be reported. You can still report it. But for, majority, this process is not very unrational unless an industry association kind of gets in and messes with it. But by and large, if the product has an electrified component or consumes electricity in the use phase, that those values are going to be communicated within the EPD. Now, whether or not databases like EC3 and others pick up those use phase information, that's a different story. I think they're moving in that direction, but I think in time we'll get better about recognizing and understanding the data that's available in EPDs. And then a manufacturer can still publish an EPD under ISO 21930, regardless of a PCR. So if a PCR doesn't feel right for your category, there's alternative options for how to do that. And some would criticize me for saying that, but it's a perfectly logical pathway.
very good. Thanks for all that, Will.
Yeah.
So within the 2040 challenge, if your firm decides to become a signatory or a supporter of the 2040 challenge, we really want you to get involved in the work of making sure that the 2040 challenge is successful. So we've come up with essentially 4 working groups that are devoted to actually helping people achieve the goals of the 2040 challenge, that net zero operational carbon by 2030 and net zero whole life carbon by 2040. So that is the 4th pillar of the challenge, is be participative. Get in there and help find solutions to these really significant issues that we're facing as an industry. So the first working group is communications and resources. That's basically getting the message out of what the 2040 challenge is, helping people get to the sources of information. They're going to be responsible for making sure that our quarterly forums, the first one of which happened last week, and we'll see another one hopefully in June, and becoming that ability for, at least virtual face-to-face exchange of information. The data analysis and reporting group is really focused on that first pillar, that the company plan and how you do the reporting. And this is going to help the industry figure out how to make those conscious decisions. It's going to help us deliver the data. You put together tools that help us figure out what those refrigerant impacts are, for instance, and then help us determine how we want to report, because at some time in the future, not in the first couple of years, but in sometime in the relatively near future, we're going to want to do what the architects and the structural engineers are doing, and that's aggregate data from the different member organizations so we can kind of see how we're doing as an industry. We don't necessarily, and we don't ever want to disclose an individual firm's data without their permission. It's really up to an individual firm to let people know how they're doing against their goals that they've established for themselves in getting to those ultimate 2030 and 2040 goals. The next one is partnerships, and this is our outreach into the building industry, into the architecture, engineering, and construction industry. It includes getting out to professional and trade organizations, academic institutions, especially building owners and operators, because as soon as building owners say that we want low embodied carbon in our buildings, then everybody's going to want to know more and do more about it. So we really want to engage with our building owners and operators to get them to do the asking of these measures to reduce the carbon associated with our buildings. And then our contractors, manufacturers, once again, they are our partners helping us achieve the goals that we're setting out. So we want to put together some strategic partnerships and get those folks into the conversation as much as designers talking to themselves. And then finally, the manufacturers and the EPDs, we really want to help the manufacturers and trade organizations understand what kind of information we need. One of the things that we're already starting to try to have conversations is, how can we accelerate the EPD information process? And rather than maybe concentrating on product-specific EPDs, if we could get industry-wide information, we might get that delivered to us more quickly for a generic chiller, as opposed to, the Acme chiller and the Zenith chiller and the Group Z chiller. If we could at least get our fence around some of that product, not products item specific, but product category specific information, we might be able to accelerate that information exchange. So that brings us to the question and answer period that I think, given the huge crowd that we've got in attendance today, we may have to put those questions and answers off to a separate time, but I'm willing to open it up, Katie.
Sure. Thank you, gentlemen. I think in the interest of time and respecting everyone's schedules, maybe we'll just stop it there. But I do encourage you all to join the LinkedIn community, CLF Nashville Hub. I believe Kim, Cory, and William are all members there. So if you have a follow-up question, feel free to engage there. Thank you so much for the excellent deep dive into MEP 2040. I personally learned a lot from this conversation and appreciate your time. So thank you all so much.
Thanks.
Thank
Thank you all.